Afternoon. Um, uh, this is accessible to everyone. This interview with Professor Israel Halpern, but I thought you might be interested in just hearing a bit more about it now. From it now. So, Albert Tucker is asking Israel Halpern who he took the courses from, whom he took courses from, and so Halpern is he mentioned courses given by Eisenhardt and Eisenhardt's course. I got rather fed up in spite of the fact that Eisenhardt was the dean and a stern-looking gentleman, and I just didn't go to lectures after a few. The other courses were so casual that I sort of dropped out of them too. I went to Bone and Blues lectures for a while. I had had most of the stuff from Professor William J. Weber in Toronto. So I met Professor Weber, but I didn't meet Professor Singh. But the one person whose lectures I had not had before was von Neumann, and I wouldn't have missed any of that. Tucker, what was he lecturing on that year? Well, I recall the story I heard later. Someone is said to have asked Eugene Wigner. How many people are familiar with the name Eugene Wigner? Just one person run into the name. He's Charlie. Jack, can you say what you know about Eugene Wigner?
I did a lot of contributions to quantum mechanics. There's like a bigger formalism of quantum mechanics, like bigger quasi-probability distributions.
What about distributions?
Well, like the bigger like quasi-probability distribution, like a way to like represent like a quantum system that's like not a function formulation.
Okay. One thing I associate his name with is the conservation laws. And the idea that well, the idea of groups altogether in mathematics, in mathematics applied to physics. In fact, here's an article you can look up, just like this one, and you only have to look. It's the title of a paper that Professor Wigner wrote. And it's a famous enough paper, and the title is distinctive enough. Just to type in the first two words. First word is not enough. But first two important words. Then it comes up. We test it now. Of course, I have to give you some words. I mean, if you just type in Wigner, it might come up. But W-I-G-N-E-R. But the paper, some of you might have heard of it. Well, without even remembering the name of the author. It's the first word is thus, so I'm not counting that. The next two words are unreasonable effectiveness. The unreasonable effectiveness. This is such a brilliant combination, such a ridiculous combination of words. But there's a workshop at the Field Institute this week on what's called free probability, closely related to but then embedded but one of the titles of one of the lectures begins with those words, unreasonable effectiveness. Obviously, that's a quotation. It's a reference, okay? So why this is it's the unreasonable effectiveness of mathematics in the natural sciences. Okay? That's the title of this thing. And Wigner and von Neumann were went through school together in Hungary. They both ended up with Princeton. Okay, so someone is said to have asked Eugene Wigner, what is von Neumann lecturing on this year? And Wigner replied, I don't know what he'll call it, but it will be Hilbert spaces. Well, von Neumann more or less invented Hilbert spaces. One of his he's responsible for the axiomatic formulation of Hilbert space. Yes, he was lecturing on Hilbert spaces, on the spectral theory. How many people know the spectral theory? Okay, by the way, look. You have a first-year course in linear algebra. It often includes something called the spectral theory. So we're talking about language, right? It's not always called that. Might be just called the symmetric real matrices can be diagonalized. Okay, it works with complex matrices too. They're only with all the ratios. When the Hermitian symmetric mean? In the context of star algebras, it's the same as self-adjoint. And the matrix and the matrices form a star algebra with the conjugate transpose as the star operation. And in fact, the C-star algebra, take the well, there exists a norm which makes it C-star algebra always a unique norm. Because that satisfies all the atoms. Okay, but the spectral theorem, and by the way, when it can be diagonalized, that's by means of the unitary matrix, right? There's an orthonormal basis. Another way of saying it. There's an orthonormal basis consisting of eigenvalues. Right? Oh, not on the camera. Yeah. The spectral theorem in finite dimensions is very important. It's related to why an ellipse is such a fundamental idea. The idea of an ellipse is so fundamental. If you transform an ellipse by a linear, so saying something is an ellipse, it's sort of, you think of it as a Euclidean notion, right? But if you take any linear transformation of the plane, then it transforms an ellipse into another ellipse. Right? Everyone aware of that? Well, the proof, I think, I would say, involves a spectral theorem. Or if you prove it some other way, then that's a proof of the spectral theorem in 2 dimensions, 2 real dimensions. And well, not only is there a spectral theorem in finite dimension, but there's a spectral theorem in an infinite dimensional Hilbert space as well, real or complex. And in fact, if you apply it, well, in the real case, if you apply it to self-adjoint operators, even in 2 dimensions, if you try to state the spectral theorem for a normal operator, in a complex case, it's true for what's called a normal operator, commutes with its edge, right? But in 2 dimensions, if you have a rotation is a unitary operator in 2 dimensions. Right? It preserves the norm. It's bijective, it preserves the norm. But I don't think it has any eigenvector. In 2 dimensions, I don't think a rotation has any eigenvector whatsoever. whatsoever. Well, if it's a rotation by 180 degrees, then it has lots of eigenvectors. Yeah. Otherwise, none. But still, there's a version for normal operators. So, and in the case of the complex Hilbert space, it is even finite dimensional, then the statement works for normal operators too. There's an orthonormal basis, basis of Hilbert space basis. I like to call it, in which if you look at the operator in that basis, the matrix is diagonal. And that's, by the way, we've been talking about K1 of the complex numbers, right? Well, that means you look at matrices, look at the vertical or unitary matrices. And you say that the K1 group is 0, that means that everything is connected. Every invertible matrix is connected to the identity matrix, possibly through larger matrices, possibly in the embedded in the left-hand corner of larger matrices. But in fact, it's true without just inside a given matrix algebra. You look at the 2 by 2 matrix algebra or 200 by 200 matrix algebra. You look at a unitary or vertical matrix, then it's connected by a path in the inside the group of unitary or invertible matrices, whichever you're talking about, to the identity matrix. Is everyone aware of that? Well, if you're aware of that, you must be aware of the spectral theorem. Because I don't know any other way to prove it. Right? If you know the spectral theorem, then it's enough to look at a diagonal operator in the complex case. Every unitary operator is unitarily equivalent to a diagonal operator. And if it's invertible, we have polar decomposition. It's equal to a unitary operator times an invertible positive operator. Invertible positive operator is clearly connected to the identity matrix. You just take a linear path connecting vertical positive operator to the identity matrix. Everything along that straight line path is positive and invertible. It's a path connecting it to the identity. You only have to look at the unitary operator is normal, so it's unitarily equivalent to it doesn't affect whether it's connected to the identity. It's unitarily equivalent to a diagonal operator. But then you just look at the diagonal entries separately and connect each one to the number 1. Right? That makes sense? Okay, so that's how important the spectral theorem is in this course. Probably we could give the whole course just by going through the interview. Well, Halpern is bringing things back to a fairly elementary level. Don't forget he's just got a master's degree in drone. And this was almost 100 years ago. Things were maybe some aspects of education were more thorough, but probably the curriculum wasn't as advanced as it was. After all, this is a 4th-year course, and the undergraduate course. Okay, at first I couldn't understand how you could have Hilbert spaces with complex numbers. But does everyone, this is out of date, right? Does everyone now understand how you can have a Hilbert space with complex scalars? Yeah, so what's the inner product? If you just take the complex numbers, that's a one-dimensional vector space, right? What's the inner product? There is it.
Like if it's X interpolate by X times my part,
Yeah, so the x and y are vectors, right? They're complex numbers, but you can multiply them and you can take a complex conjugate. And so if you do that, then you get an inner product. Maybe you should say you take the conjugate first. And then, you just conjugate one. Okay. And have you checked that gives you the axioms of a Hilbert space? Okay, well that's a good, maybe you should do it. For instance, if you get a norm, what's the norm of a complex number? Considered as a vector. What's the length of the vector? Well, it's supposed to be a Hilbert space, right? So you need to have a length, a norm. Every vector has a norm. If it's a one-dimensional complex vector space, if you think of it as a vector space of complex number, what's the norm? Well, in general, we know it's expressed in terms of the inner product, right? You take the inner product of the vector itself, so it's x times x bar, and then you take the square root. Okay, but that already has a name. If you look at complex vectors in the plane, and what's that number? Sorry? Look, if you have one-dimensional complex space, we can visualize that as a two-dimensional real vector space, right? And there's in two-dimensional real vector space, there's also an inner product, right? How do you get? What's the formula for inner product in the real one? You take two vectors x and y, you have x is x1, x2, and y is y1, y2. And what's the inner product?
X1 squared.
X.
X1 squared.
Well, that's the norm.
Yeah.
That's the inner product. That's if y is equal to x, that's what you do. What do you do if x is not equal to y? Sorry?
Take off from.
Well, okay, does anyone want to actually voice the formula? Yes.
So if x is x1, x2, and y is y1, y2, then the inner product would be x1 times y1, then plus x times y2.
Okay. And and that's a real number, right?
Yeah, yes.
And how does that relate to the complex inner product of x and y?
So in the complex case, you'd want to conjugate the entries of y
Yeah, yeah.
and then just take the dot.
Okay, so it's a complex number, it's not a real number.
Yeah.
Well, okay, but is there no connection whatsoever between the real inner product of x and y, considered as points in the Euclidean plane, and the complex inner product as considered as points in the complex, one-dimensional complex plane? Is there a relationship? Larry, do you know a relationship? Well, you have you have two sets. One is a one-dimensional complex vector space, and it's a Hilbert space. It has an inner product, which is a complex number. And then but it's also a real vector space, two-dimensional real vector space, and it has an inner product, real valued inner product. So what's the relationship? How many people are aware of the relationship between these two inner products? So?
I guess they have like.
Sorry? I mean, once you have the formula for the two inner products, then you can just say that the relationship is on the one hand, one of them is this, and on the other hand, the other one is this. And sometimes, and that might be the best you can do, right? But I would say in this case, it's not the best.
If you restrict the complex dot product, you don't just real dot product.
So yes.
When you restrict the complex inner product to real numbers, it
Yeah.
just gives you the real inner product again.
Okay, but what does that mean?
That means that the real inner product is just the complex inner product restricted to.
Okay, but what's this restriction do? Because the vectors are the same. They're either in their points in the plane. they have the same pictorial representation, points in the plane x and y, or points in R squared, x1, x2, y1, y2. The information is exactly the same. So seems to me you're giving rather vague connection between the two. One is a complex number. Just maybe it's possible to say that one of them contains more information. I suppose a complex number, if the inner product is for the complex vector space, complex vector space, that's a complex number, then maybe it has more information than the inner product for the points in the Euclidean plane. It's the same points, but maybe the complex inner product contains more information, possibly.
Are we relating complex plane to the real plane, like R2?
Well, yeah, I mean, geometrically it's the same thing.
Yeah.
But somehow,
And
but the complex numbers are not quite the same as whatever the same. The information in a complex number is the same as the information in a pair of real imaginary part, right?
like the dot product complex plus, or it can be just multiplication complex.
Well, in the real, yes. Remind me of your name, please.
Luke,
Luke, okay, good.
I was gonna say that,
And so we have two inner products, right? We have the real inner product, and the complex inner product.
I was gonna say that the real part of the complex inner
Yes.
product is the dot product.
How many people does that bring about? Okay, and okay, good. And if you haven't, you're not aware of it, maybe you want to check it, right? Just write down write down x times y bar, the terms of the x1 and x2 and y1 and y2, and see if the real part isn't equal to x1, y1, y2. Okay. And then there'd be a question: what's the complex? What's the imaginary part? What's the vector? But and what's the addition from a geometrical point of view in the plane? What's the additional information? So to these 2 points in the plane, then the real inner product will give you a certain information. The complex inner product is supposed to give you more information. From a geometrical point of view, how much more information? How do you visualize? You visualize that additional information. For instance, I guess it's well known that the inner product. Yes, John. You're going to say something?
Actually, sorry.
Okay, good, good. But I guess everyone is aware that some kind of inner product is supposed to say something about the angle between the two vectors, right? Yes.
No, I was just gonna say, I think it's like the imaginary part is the negative of the determinant, or like I guess the area of the
negative of. Negative of. You say negative. That's good.
like the negative
Yeah, be negative
of the determinant. And
of
by
the
the
which?
like
Discriminant.
the determinant, yeah.
Okay, well, that's, yeah. The discriminant is, that's something to do with the parallelogram. Look at the area in the parallelogram. Well, yes, well, yes, yeah.
If you change the order, I mean, if you put second point x prime and y prime first in the matrix, the determinant, and the minus will be no problem. If you put x prime and x1, y1, and then excuse me, x2, y2, x1, y2, then we don't have a minus. Then it will be the determinant example.
Okay.
But
This elementary geometry is something that I should be reviewing all the time too, right? But let me just wind up that mini discussion with repeating the question: what is the norm? So we agree it's the square root of the inner product of the vector itself, which is part of the real number. Before you take the square root, and then you take constant square root. That's from a geometrical point of view, what is the norm? It's just the length, right? Length of the vector. Okay. That's the same. That's the same whether you're looking at the real vector space or a complex vector space. And the real inner product. Well, okay, but you could almost write an essay about finite dimensional inner product spaces, comparing the real and the complex one. With respect to their and what the applications of the theorem. I guess if you have an ellipse, you want to find a major and minor axis. I guess that's the spectral theorem. And it works in higher dimensions too for ellipsoids. I think that this is considered to be important in engineering. And by the way, the spectral theorem in infinite dimensions, which is what is definitely going to be useful in this course, if we haven't used it already. Well, there aren't any eigenvectors in general. Okay, so you have to make do without eigenvectors. There's a and it should be a similar. It has to be a common formulation that covers the finite dimensional case and the infinite dimensional case, right? So somehow you need to find a way of formulating the spectral theorem even in finite dimensions. It doesn't mention eigenvectors, doesn't mention eigenvalues. Okay, that's a good exercise. Let me give you a hint. Well, let me do it because it's it may not be clear why you should do it. But let me give an expression. Let me give a formulation of the spectral theorem in finite dimensions for a finite dimensional, say, well, real or complex. We talk about self-adjoint operators. The real and complex Hilbert space statement is the same. And then see if you can make sense of this for an infinite dimensional Hilbert space, a bounded self-adjoint operator on an infinite dimensional Hilbert space. Okay, so I'll state it for a finite dimensional. Well, so whenever you have a measure space, you have to know what a measure space is. Okay. Whenever you have a measure space, then there's L2 of the measure space. You have the L2 space for the measure space, and that's a Hilbert space. Okay. There's a natural, in terms of the measure, you have two functions, you can define the inner product. So in the case of one-dimensional space, if the functions are just, if the measure space is just a single point, then the functions are just single complex numbers, right? So the inner product is, if they're just x and y, then the inner product is x times y, because the integral is just evaluating it at one point, just giving you the value of the function. That's what the integral is. Okay. So so we're generalizing this. It generalizes the one-dimensional complex case. So you look at the L2 space in general, and if you have a bounded measurable function, real valued function, bounded real valued measurable function. You have an arbitrary function on the measure space, measurable function, of course, L2, arbitrary L2 function. If you multiply that by a bounded function, you get another L2 function, right? And if it's a real valued function you're multiplying by, it's a bounded real valued function you're multiplying by, you get a bounded self-adjoint operator. Okay, but the fact that it's bounded, I mean, if it's a finite, if the L2 space is finite dimensional, that says the measure space is finite, okay, finite set of points. So really, and L2 functions then are vectors, right? They have, they just, for each point you have the value of the point. That's like the coordinates of a vector. And a bounded vectorial function is just another, it's another finite set of numbers, right? Finite set of real numbers. And multiplying the two functions, that's just multiplying the the easiest way to multiply them is to consider them as diagonal matrices and multiply them as matrices, right? That multiplies the corresponding values of the functions. So if the diagonal matrix, the function, if you have a function, you put the values of the function down the matrix, and that tells you what it is as an operator. Okay, so that's the correspondence. But, you know, the trouble is I couldn't state the finite dimensional theorem without stating the infinite dimensional theorem. So the exercise is thrown out the window. You could prove it, okay? You could review the proof in the finite dimensional case and then see what you need to prove it in the infinite dimensional case. That your given bounded self-adjoint operator is unitarily equivalent to such a multiplication operator or by bounded measurable function on the case on the L2. By the way, you might want to think about it. And in fact, there's a way of proving this theorem in the infinite dimensional case, just applying the finite dimensional theorem. You prove it using the finite dimensional theorem. Of course, you still have to prove the finite dimensional theorem. So maybe it's simpler to prove the infinite dimensional theorem from scratch. That includes proofs of the finite dimensional. Life involves choices, right? And you can't always have it both ways. In this case, you could. Maybe that's enough of the interview. One thing. That's what that's I feel like that's one day, one minute in the life of Israel Hubble. By the way, he has a nice proof of the spectral theorem in it. There's a paper in the 1964 American Mathematical Monthly giving a very elementary proof of the infinite dimensional spectral theorem, which works for the finite dimensional case too. You don't have to assume the finite dimension. There are two, Professor Halpern has two papers in that journal, the American Mathematical Monthly, around in the early 60s. And this is just one of them, 1964. Forget what the other one. Well, okay, so he says, I had never heard of such a thing, Hilbert spaces with complex numbers. I asked Malcolm Robertson, how do you define the inner product if you have complex numbers? And he told me, well, I know now too. Good. All right. Well, at least in the one-dimensional case. Okay, so here's a kind of a riddle, by the way. Whereabouts in the course are we using the spectral theorem? I think I've even put it in as a prerequisite for the course. And is this purely a psychological thing, or is it something that actually gets used? Okay, so we were discussing the what period is, and I like to start from a schematic outline. And sometimes people think my schematic outlines are a little too schematic. But I'd like to feel that there's no such thing as too schematic, okay? As long as you prepare to stand by whatever you're closing it back out. Okay, so first step is go to that, okay? At the level of we're talking about idempotents and vertical elements, or projections and unitaries. If we're not going to be able to stay with projections and unitaries forever, we might as well start off with more general, more abstract, non-star structure idempotents. This is the this is the T square. So what was the invertible? Well, we want invertible. We're looking at a map from idempotents to invertible elements, right?
Yeah.
Vertible elements of the suspension with unit adjoint. Well, yeah, what you're saying is suppose that P were equal to 1. If P were equal to 1, then what would the what would we be taking?
TAP.
What's A?
T.
Oh yeah, well, come on. That's too trivial. We want something that has this is a non-trivial case. It's not 0 would be the 0 K0 cost. This is in general, this will not be the 0 K0 cost. This will be an interesting K0 cost. In the case of the complex numbers, this generates K0, right? Okay. So it would be enough to look at this case. And it's supposed to somehow suggest what the general case is. But in this case, what's the invertible element or unitary, if you like? This is a star idempotent, this projection. So we expect to get a unitary. Right? What would the unitary be? In the so we're going from A to suspension of a tilt. Well, it's not a map of algebras. We compare the two algebras. We go from K0A to K1. K1 in terms of invertibles or unitaries. So what Larry, what would you put here? Remember what the suspension is. It functions on the circle.
Yeah.
Which are 0 at the special point on the circle, number 1. Okay. Look at the unit circle. Then you have the special point. So the suspension, we thought it was A-valued functions, which are 0 at the special point. And if you join a unit, it's A-valued functions. Since A has a unit, it's A-valued functions, which at the point at this point, they are scalar multiples of the unit, still belonging to A, but they're still A-valued functions. Okay, so you want the function which is A-valued and is non-trivial, and it's equal to 1 at the beginning and the end of the path. And it should work if A is just the complex numbers. Charlie?
Sure. I'm thinking so.
Okay. Yes.
One, not zero, like multiples of the figure, like P and then.
So the algebra, if if A is the complex numbers, then what is S of A? In terms of, what is S of A?
The complex number, like the extended complex number. Or infinity. Or just take the point infinity.
Well, A is the C, and it already has a unit,
Right.
and the suspension is functions on the circle with all values in the complex plane. So it would be divided as a path, right? The path, and it would be in fact it's an arbitrary path because the fibers are always just scalar multiples of one. So there's no condition if the suspension would be zero. I mean, the path should be zero at the end. But if it's in the tilde, if it's SA tilde, it's an arbitrary path, continuous. It's some path, it's some element of some continuous of the algebra, continuous functions on the circle, continuous complex value functions on the circle. This and that's what S of C is with unit and joint. So if A is C, then S of C tilde is just continuous functions, continuous complex value functions on the circle. And what's the simplest non-trivial continuous complex value function on the circle? Remember, yes, Larry. Sorry? Okay, yeah, and this is a joke for it's a humorous, supposed to be a humorous description of the identity map, because the circle is contained in a complex plane. So every point on the circle is a complex number. So you take the identity, you take the inclusion matrix, the circle into the complex plane. That's a function on the circle, complex value function on the circle. And you could call it Z, or Z or Z equals, I like the joke. I think it's funny. I think it's funny to say Z or Z. Okay. That may more be a reflection on me. Okay. But if we're looking for a notation, we could say, well, we could say this. It might be slightly confusing, but I don't think it's so confusing. Another way of saying it is said, and so this is accurate. This is kind of abusive notation. Z is a single complex number, and of course you say Z equals Z, and it's obviously the identity map, right? That's what on any space the identity map is X of X equals X. You could write it as X. X marks the spot. There's I keep thinking about George Gamow, book 1, 2, 3, Infinity, which I read when I was maybe even a preteen. I forgot. That's still a word. And there's one of the items in the book. It's very interesting. It's about the importance of complex numbers. Someone found a treasure map about the buried treasure. Have I told this story? Buried treasure on a certain island, which is the guy knew where it was, so he went there. Then when he tried to follow the map, one of the things on the map you were supposed to orient yourself by, make a turn, make a left turn there, was an old wooden gallows. His pirates. I guess the pirates they buried the treasure that got caught. Anyway, the trouble with following the instructions on the map was the gallows had disappeared. It had rotted away. But the guy had studied complex variables, theory of complex variables. So he was able anyway to find the treasure, locate the X on the map. Okay, and so you could look it up. Got to guess how it might work, or you could look it up. It's very ingenious. That's what I do recall. Okay, and it's 1, 2, 3 infinity George Gamow. He's one of the most famous physicists because he discovered, have I mentioned this? I told this story. He discovered what did he discover? He discovered, nowadays, everyone knows that the sun is hot, right? And it's not just a fire. So he found out why the sun is hot. Okay? And it's quite funny. You see a bumper sticker that says, it has a picture of the sun on it, and the sign on this bumper sticker says, "Atomic power, no thank you." Okay, but this discovery was joint with a student. Have I told this story? It's almost worth telling. The student is still alive, and he still complains about this. What happened? So Gamow was mischievous in many ways. When he in the 50s, when he was looking to leave the Soviet Union, he gave an interview lecture, public lecture at the University of Colorado. The physics building there is named after him. And at that time, there was there are always funny things going on in Russia. That's former Soviet Union. The then present was the former Soviet Union. In those days, one funny thing was there was someone claiming to be a biologist and propounding all kinds of crazy theories that to make about genetics, to make meat strong, you should sow it on top of the snow, things like that. And but this was reinforced by Stalin. So if you disagreed, then that was it. I mean, you wouldn't have any job. That would be the least. That would be the least. Okay, so so Gamow began his lecture by referring in a very respecting manner to his colleague. His name slips my mind just at the moment, but it doesn't matter. Maybe it's better not to be repeated. But my worthy colleague has come up with has discovered very important facts and so on and so on. And you could see how, but everyone outside Russia was aware that this was nonsense, and so you could see how people's faces fell when this visiting public, this supposedly brilliant public lecturer, was starting to talk about starting to play to boost his Russian colleague crazy pseudo-biologist. And but then Gamow went on. His magnificent theory will explain the following phenomenon: that if it happens in a family, if the son looks more like the milkman than the father. Okay. Well, when this saved the day, he got the job. Okay. Got the house down and got the job. Okay. So in 1, 2, 3 infinity, he talks about complex numbers. Well, we talked a bit about complex numbers today, and I've almost covered the spectral theorem. You should know now. You should know how to state the spectral theorem in a way which is consistent in both both the finite dimensional case and the infinite dimensional case. And also you should know how to prove it. You either look up this 1964 paper and it's just using it's easy lemma on ordinary polynomials, okay? Lemma of ordinary polynomials in the line. It reminds you a bit of, it'll remind you a bit of Pascal's triangle. And so that's so you get the ordinary spectral theorem, and then the infinite dimensional one. And you can, if you want, you don't want to look up the 1964 paper. If you don't want the high school lemma of polynomials, then you just use the spectral theorems for finite dimensions, which is not that hard to prove. That's a high school exercise too, possibly. And you apply that to the infinite dimensional case to use the spectral theorem to the infinite dimensional case. Now the strategy for that might be a little you might not hit upon it yourself. Might not hit on it yourself. So if anyone wants to hear about it, then we can talk about that in the future. By the way, how many people want to have a make-up Monday on December 7th?
Like at the end of the semester.
Sorry?
At the end of the semester. At the end of the semester.
Yeah, on December 7th. Yeah.
Yeah.
It's a make-up for a legal holiday. It's a little strange. Why not make up for Sundays? But anyway, we could have one and we could talk about the spectral theorem.